So now, moving on to the stuff we have to actually cover. Yeah. Ready? Yeah. So, given a, I make these typos and I don't know why Joel didn't catch it. Given a think plate, that's supposed to say thin plate. So this is the question we're going to answer with today's lesson.
It says thin plate.
Okay, I didn't fix my beamer then, that's the problem. So given a thin plate of uniform density and any shape, how might we find the point P on which this thin shape will balance? It's going to be easy if you have this, say a clipboard, the balancing point is just the middle of the horizontal and the middle of the vertical. Does that make sense? Barring this part that's heavy here on the end. So we're going to have some random weird shape and we're going to find the balancing point of it. So the first thing we're going to consider is the one-dimensional discrete case. We're going to do this in two parts, and I'm going to change how I do this. I'm going to go over the easiest part, do example one, and then go back and do the other part of the derivation. So the first case is if you have a lever. Like think you're playing seesaw and you're still 5 years old, okay? So you have a kid over there of mass 1 and a kid over there of mass 2. Poor kid. If the seesaw is going to balance, who does it have to be closer to?
Mass 2.
It has to be closer to mass 2, right? So there's the fulcrum of that seesaw. And suppose this is distance 1 and this is distance 2. So what the law of the lever says, this will balance when mass 1 times distance 1 equals mass 2 times distance 2. That's an I and it's not supposed to be, so let's white it out. Does that idea make sense? That's how you find the specifics of where that point is. Okay. So let's use that to do example 1. Okay? So in example 1, we have a 20-pound child and a 60-pound child, and they sit on a seesaw that's 5 feet long. So who are we going to put in the left? Doesn't really matter. The 20-pounder, okay. And on the right, we're going to put the, maybe they're different ages, it isn't just the Cheetos, okay? So, all right. And the fulcrum's obviously going to have to be somewhere over there, but the question is exactly how far to make them balance, right? Okay. Is everyone okay with that much of the setup so far? Okay, I'm going to pick a distance, so from a kid to the fulcrum, I'm going to call that x. Doesn't matter which one, I'm just going to call this one x. Your WebAssign might define that a specific way, it might say, call x the distance from the littler kid to the fulcrum, just watch out for stuff like that. And if I let that one be x, this one is, 5 minus x. Does that make sense? And then the law of the lever says mass 1 times distance 1 has to equal mass 2 distance 2, or 20x equals 60 times 5 minus x, right? And from there, it's not very hard to solve at all, is it? So you have 20x equals, what's that, 300 minus 60x. 80x equals 300, and therefore x is equal to 8/3. Which is what, 2 2/3 meters, right? Did I say what? 300, there we go. But I think, so 80/3 then?
38.
I was just testing you guys. 38th, arithmetic, all right? I was just talking about 15/4. Which is, I don't care. 3.75? Yeah. Okay. Sorry, guys.
So, but do you have to say 3.75 meter or feet from the small child?
You should specify, yeah. Although, if you have a picture that's labeled with what your units stand for,
Yeah.
it's also feet. Okay. Yep. You guys are passing lots of tests this morning. Yep. And you probably should specify from the small child. If you have a picture that's labeled, that's also good enough. Okay. So that part's not very hard, is it? No. Okay, now we're going to generalize it to, suppose we have like points on the x-axis anywhere, and can we get a formula to find out what this is based on what the masses are? So just go back up to the top where you have some space, and I'll do that right here. So second case is suppose your rod, or your seesaw, for example, lies on the x-axis. And we're going to let x bar equal the center of mass. So what we have here is a one-dimensional picture. Kind of hate it when I can't draw straight lines. Okay, so there's x1, here's x2, and at x1 is mass 1, at x2 is mass 2. And the question is, where is that x bar? Can we get a formula for it is kind of what the question we're trying to answer here. Okay, is everyone okay with the picture? Yeah? Okay. It's just you have your seesaw is just laid on this axis, that's all. You could have laid your seesaw from 0 to 5, for example. Okay. So what would this distance be from x1 to x2? How could you find that? Or x bar. How could you find that? X bar minus x1. Exactly. And then how about this one? X2 minus x bar, exactly. Good job. And then from knowing that, can you apply the law of the lever? So when you apply the law of lever, what must equal what?
Mass 1 times distance 1.
Mass 1 times distance 1. And distance 1 is x bar minus x1, right? Has to equal mass 2 times x2 minus x bar, which is distance 2, right? Does that much of setup make sense? Okay, we're going to take this equation. We're going to solve for x bar, because that's the point on the x-axis that's going to be our x balancing point. So I think the first thing you should do is distribute the m1 and m2. So m1 x bar minus m1 x1 equals m2 x2 minus m2 x bar. Is everyone okay with that? Okay, and if you're solving for x bar, get the x bars on the same side and the non-x bars on the same side. So we put the x bar things on the left. What things have x bar? M1 x bar plus M2 x bar, there's no reason for parentheses there, I just made a typo and fixed it, is equal to M1 x1 plus M2 x2, right? And then you can take out x bar. And finally, x bar is equal to m1 x1 plus m2 x2 over m1 plus m2. Is that all right? Okay. So this top thing, this is called the sum of the moments. This bottom thing is called the sum of the masses. Or you could call it the total mass. And your book, I think, also proves this if you have like 3 things or 4 things on that axis and still trying to find the balancing point of them. Like if you had 3 kids on the seesaw, where would you put the fulcrum somehow? But not like 2 concentrated at one end, at random places in the seesaw. How would you balance that seesaw? And what happens when you add in 3 things or 4 things or 5 things? This pattern stays. It's like if you had 3 things, I'd have M1, X1, M2, X2, M3, X3. That'd be what the stuff that's added to my numerator. all divided by the sum called masses. That generalizes to if you have more than two things. It's just that it gets tedious to do the solving. Does that make sense? Okay, so we're going to use that to actually find the center of mass thing for example 2. Okay, so you have 3 masses lying at the points x1 is -5, x2 is 1, and x3 is 3. So there's -5. At that one we have mass 1, which is 7. 0, I'll call that at 1. We have mass 2, which is equal to 3. And at 3, we have mass 3, which is 5. And you think from -5 to 3, you have your seesaw, and then you have weights on it of 7, 3, and 5, respectively, and where are you going to balance that seesaw? It's the same idea, except for people that aren't at both ends, there's somebody in the middle as well. Does that make sense? Okay. So the way you find this center of mass, which is called x bar, I'm going to use some fancy notation here. You've seen that sigma sum before, which means add up. You add up xi, mi. So by xi, I mean like all of the x points, right? Mi is the masses, right? Okay. All over what's in the bottom? Sum of masses. And of course you've seen that sigma symbol, duh, like we've been doing in like Constantine's class. Like I don't know why I asked that. Okay. So how many things are you going to be adding up in this particular case? 3, because you have 3 masses, right? So first, mass 1 times mass 1's location is 7 times -5. What is mass 2? 1. What is its location? Oh, sorry. I have that backwards. Its mass is 3. Its location is 1. But either way, it doesn't matter, right?
Calculus even be possible without the sigma?
You just need a new symbol. 5 times 3 over. What numbers get added for the denominator? 7, 3, and 5? Yep. Okay, great.
And you can't just factor those out, right?
No, that would be the kitten killing cancellation. Definitely. Yes, it would. So -35 plus 3 plus 15 over 15.
Plus you.
Gesundheit. I think that ends up being -17 fifteenths. So that's where the center of mass would have to be to balance out this system. And that kind of makes sense because you got the heaviest thing on the left side, right? So it makes sense maybe you're going to have to go a little bit to the left of 0 to make that balance. With the seesaw question, just going back to that for just a second, you could have drawn the seesaw like on the axis and said, okay, there's 0, here's 5, my x bar is in the middle, and mass 1 is kid 1 who was 20, kid 2 who was 70, and you could apply the same system. Does that make sense? You don't have to, but you totally could. Alrighty. Okay. Now, the two-dimensional discrete case. Now, suppose instead of just like one thing, we have like planets. Has anybody, who's a Doctor Who fan? Anybody besides me? Oh, I'm sorry if there aren't enough. Remember the planets in the sky thing where the planets all like came out and balanced perfectly? That's what I think about this. Okay, and I should pull up a video clip sometime of that happening, all right? But anyhow. So the point is you have masses. I'm going to draw a little picture here. So there's my mass 1. I think it's helpful to think about them as planets. There's planet 1, and this is y1, this is x1, right? It's over x units enough y units. Maybe somewhere down here you have mass 2, and that'd be x2, y2. And say back here you've got mass 3, and that's x3, y3. And you want to somehow balance, like figure out, okay, if I had these planets, what would be kind of like the balancing point of this system, assuming they're connected by like rods or something that are holding them in place, right? Like you have to kind of assume a a seesaw, we're figuring out where am I gonna join the seesaw things together. By seesaw, I mean there's gonna be like a seesaw for 3 kids with a joining point in the middle someplace that would allow them to then balance. Okay.
How that work?
Well, you kind of look at it 2 cases at a time. What you do is you first, and I can't do this with my PowerPoint thing, but you balance it, you figure out what's gonna be the balancing point in the X direction, and then you find the balancing point in the Y direction. And then that coordinate is the balancing point of the whole system.
That makes sense.
Does that make sense? So you balance it one way, and I think if you were trying to like do the same thing with like this kind of object, you'd balance it this way, and then you'd balance it this way, like does that make sense, like this? And then you'd look for, okay, well where do those 2 things intersect? And that would be the balancing point. Same idea. Now here is where the notation is just, I find a little bit annoying because it's not what I think it should be, but I have to be consistent with the book, okay? So what your book defines as my, this is a sum of mi times xi from 1 to n, where n is how many things, planet, pieces, children you have.
Is that N on the top?
That's an n on top, yep, for n being how many. Now this is called the moment about the y-axis. And I think what they're thinking there is what you're doing is you're kind of fixing the y-axis and we're finding the centering point that way. I mean, I find the notation annoying because I think that this is going to find the x direction, so it's using the x's, and I think that seems backwards to me. But your book does it this way, so just suck it up and deal with it, okay? Because they're going to ask for questions where they ask you to give my, and you got to know that's the x part, okay? So I'm very sorry, I won't, on your test, there's a way to get around this, and I'll teach that to you, okay? Because I also hate it. And then mx, what's that going to be? How is that going to be different?
It's gonna be y.
It's just going to be y's, exactly. mi times yi. And that's the moment about the x-axis.
Wait, should Y equal N, or no, Y, I, not below the signal?
I should equal 1 on the bottom, yeah. Sorry, I from I equals 1 to n. Just got going a bit too fast there. Okay, so then x bar, and let's let m equal the sum of the masses. Does that make sense? Just add up all the masses. And then you find your x bar the same way we found x bar before. So x bar would have come from taking whatever this my expression was, right? Divide by the total mass. So that will be my over little m. And then y bar will equal mx over little m, right? So I'm sorry that the formula is like, what makes me cranky is that the formula for x bar has m subscript y, and I don't like it, but it just is what it is. Does that make sense, though? It's the exact same as the other case, it's just you do 2 of them. If you had a 3-dimensional system, you would do 3 of them, probably. Not this class.
But then you probably have to do reiterations because in the 3-dimensional system there will probably be things you hadn't factored in.
I'm not sure. I just don't know. I haven't done Calc 3 in a long time, so I don't remember, but I think it might just generalize. But I'm not positive. Okay, so let's find the center of mass for this system. So we're given masses and we're given points. So x bar, I know, is my over m. Okay, I got m was 37.5. How did I get that? Just added those things all up. Does that seem like probably reasonable? 25, 27 plus 10.5. Okay, yep, we're good. Okay, so then the thing to remember with my is that's the sum of mixi over m. So take mass 1 times its x coordinate. So mass 1 is 12, its x coordinate is 2. Mass 2 is 6, its x coordinate is -1, right? Is that okay? What's mass 3? 4.5, and its x coordinate is 6. And then mass 4 is 15, x coordinate 2, right? All that business divided by 37.5 ends up giving you 2 for x bar, okay? I'll just trust that you can arithmetic given proper time. Is that all right so far? And then y bar is the same thing, so it's mx over m, which is the sum of masses times what coordinate this time? The y coordinate, right? Still divided by total mass. So mass 1 is 12, its y coordinate is 6, y coordinate 5, 4.5, y coordinate 8, and 15, y coordinate -2. All divided by 37.5 comes out being 144 over 75.
Well, that was significantly larger.
I think it's actually not. I mean, it's 175, 75 times 2 is 150, right? So this is awfully close. It's a little bit less than 2, right? Do you agree with that?
Yes.
Yeah, okay. Okay, so everyone okay with that business? Okay. So now we're going to move on to the case where instead of having discrete things, we have like a nice continuous bubble of stuff. Okay? So when you have a bubble of stuff, here's what's going to come out for those mx and my things. I'm going to show you why that's the case as well. So mx, so you suppose you have a region, R, of uniform density, and it helps me to think density is measured in units like kilograms per cubic meter, right? Pounds per cubic foot, right? So this thing tells mx is whatever that density is times 1/2 your f of x squared minus g of x squared. And the thing to notice here is that your f of x is bigger than your g of x. And mx, well, we'll get there in a second. And then my is given by this integral. And it's not totally obvious at all where those things came from, right? Okay. And then using those mx's and my's, you use my to find x bar, just like before, right? You use mx to find y bar, just like before, right? And I'll generalize that formula at the end because it turns out that the row isn't going to actually matter. It's just that if a WebAssign question asks you to find mx or my and it doesn't give you row as part of the answer, you got to put row in there. Does that make sense? If you miss that row, you're going to be counted wrong. Yeah. Oh, I'm sorry. This letter is the Greek letter rho. My bad. The problem is I took so much math, I learned so much Greek without knowing it, and now I say these letters like they're nothing. Yeah, so that's the Greek letter rho. It's the Greek R. Random aside, it's also R in Russian, which is based on Greek. So, anything else?
Why do we choose letters that are so much like existing letters?
That is a question I cannot answer. Okay, so I'm going to show you where those formulas come from, all right? Okay, moving on. All right, suppose you have this region. All right, the assumption is that you have two functions and f of x is bigger than g of x. So here's your f of x. Here's your g of x. And between sum a and sum b, f of x is bigger than g of x. And we need to balance this thing in the x direction and then balance this thing in the y direction. Yes?
Sorry, but I'm sure you'll come to this, but what happens if g of x randomly right in the middle?
We're not going to do it, okay? We're only going to consider the case where f is, there's no flipping of who's bigger than whom in this stuff, okay? We're just going to have f bigger than g. Yep, nope, not going to get there. Okay, so you've write a little bit small for this. So the first thing is to find to find the x bar and y bar, you definitely need to find the total mass, right? Does that make sense? So the first thing let's do is let's get an expression for the mass.
Would that be partly?
Nope. The mass of this like say shape. So mass is density times what? Times volume. Is that right? I have density times area written down.
Why would that make sense?
Why would that make sense? We only have a two-dimensional thing here. So density is in units like kilograms per meter cubed, area meter, kilograms per meter.
Area times height.
Yeah, you're probably adding in another dimension when you integrate. I think that's what's happening.
Are we assuming this shape has mass without volume?
Yeah, we are, because you're told that you're given a region of uniform density rho.
So in this case, it would be density times area.
Yeah, and then probably there is like a little, say that again?
In this case, it would be density times area.
Okay. So the density is rho. How do you find the area? It's not a trick question. The old-fashioned area way, which is the integral from a to b, f of x minus g of x dx. So that would be, we'll just call that rho a. So that part's easy. The total mass is rho times the area. And I suppose we are assuming that there is like a little bitty thickness. I say that says like, it says of a uniform density. So that's how we're getting the right units there, because we do have a very, very, very thin thing. Yeah.
But why is the area not one?
Because we assume that it's a region of uniform density, and we assume that's a really thin plate, so that last dimension is really, really a small number. That's why. Okay.
Or you just assume it's not possible, but just theoretically that way.
Okay, now the next thing we need to find, we need to figure out the balancing point in the x direction, the balancing point in the y. Does that make sense? So for the balancing point in the x direction, that's this my business, which is a sum of masses times your x coordinates. So you have these little chunks, because like everything you say, you divide it into little chunks. Take the chunks to infinity.
I think if you just guessed on the point, then you'd have a 1 in infinity chance of getting it right.
All right, so moving on. So, all right, so the mass of a random rectangle, you're going to find the same way. You're going to take that rho, the density, times the area of the rectangle. So let me write down rho times area. And then also area of rectangle, and then adding in the next dimension is the whole delta x business. That's where you get the third dimension to cancel out the units on the row. So these are little rectangles. And I shouldn't add the delta x in yet, sorry. What is the area of one of those little boxes in general?
X times 1.
It's a little rectangle, right? What's the rectangle's height? F of x minus g of x. We'll say f of x sub I minus g of x sub I. And what is its width? Delta x. And then you have this x sub I thing, and that came from the moment formula that told you to think, how you have to take into account how far over that piece is. So take number of pieces to infinity, and my is going to equal rho integral a to b, right? What's going to be inside of my integral? Obviously f of x minus g of x, right? Is there any, and there's a dx obviously as well, so delta x becomes, what else has to be in the integral? X sub I, and that becomes x once you've taken the limit, right? So that's where the my formula comes from. Does that match what I have above? Yeah, yes?
How did you
Say that again?
So that was the area, and then,
Yeah, this is the area of that little rectangle. And then we multiply by the density of that little rectangle, that gives you the mass of little rectangle. Like how much mass little rectangle weighs. We're assuming that there's like negligible thickness. Okay, and then how about the mx? So mx is still sum of masses. Now it's times the yi's. Okay. Will the masses change from the previous problem? No, so that's still going to be rho f of xi minus g of xi delta x. But then the question is holy moly, how about that yi? What should that be? So is that okay? So is that clear? That's the thing we're going to find. So think about this rectangle. If you were going to try to find, say, like the balancing point of that little strip, where's it going to be? It's uniform density. It isn't like it's like denser on one and then the other. So the yi is going to be in the middle, which you could find by taking the, how do you find the middle of those two y's? Find the length and then, so add them together and divide by 2. Does that make sense? You average them. Does that make sense? Yeah. So fxi plus plus gxi over 2. So then we have rho over 2 sum. When I multiply this times this, what do you get?
Wait, wouldn't the height be subtracting one from the other? Your height and dividing it by 2?
But you want to find the middle point, so that's definitely an average. So maybe your method won't work.
Okay.
Does that make sense?
Yeah.
So I do think that perhaps somehow I could make yours work, but I think it's just you want the middle point, which definitely would be the average. So when you multiply them together, what do you get? F of xi squared minus g of xi squared delta x, right? And the over 2 got pulled out in front of the sigma symbol. So then what does mx equal as you limit, go to infinity, rho over 2, integral a to b, and inside of the integral is just f of x squared minus g of x squared. Cool. So, and then the last step, which is actually summarized in your paper, but I just want to show you. If you found x bar, which 2 do you divide? mx or my? My and m. And if I take my, which was rho integral a b x f of x minus g of x, and I divide it by rho area, look at what happens to those rows. They cancel out and don't matter. Does that make sense? And this just becomes 1 over area integral a to b x f of x minus g of x dx, which is the formula given for x bar right below this big open space, right? Can you see the same thing's going to happen with y bar? So y bar is going to be mx over m. So that will be a half 1 over a integral a to b f of x squared minus g of x squared.
We're gonna have to memorize these formulas.
Those 2 you will. Yep.
I'll have those memorized before the class.
See, like
Yep.
other formulas we generally use it so much.
This one, when I give it on a test, most of the time the only thing the students miss is the 2. I mean, like, really, you'll do the homework on this tonight and you'll have them memorized, and you'll forget them when the test is over, but you'll have them memorized for at least the test. Just do it for once, then you can forget them. Okay.
Can you explain where the my, where the x sub I comes from, and the mx where the y sub I comes from again?
That comes from way back on the first page when we did the derivations.
Yeah.
So back on that first page, when we did like the second part of the derivation, for example 2, it's the same kind of general formula. Let me pause my recording. All right, so, whoop, that's not what I wanted. Cool. So there are the formulas for x bar and y bar. So this one I'm going to kind of probably, I think I'm going to not finish it all the way because the arithmetic's a little bit tedious, but we're going to set it up and then we'll talk about how you would finish the integrals once you've got them set up, and you can check the answers against the ones on on the notes. So the first thing is if you're going to find, mx, my. So first of all, let's find, and if we're going to find x bar, y bar, we need the area. Does that make sense? So I think the first step you should do is find the area.
Not find the mass.
Oh, and then the mass is going to be rho times that area.
Yeah, good point.
Yep, so you'll need the area to find the mass. So the area is equal to the integral from, well, let's graph that curve. So we have e to the 2x, looks something like that. Y equals 0. So x equals 0, y equals 0, x equals 1. That intersection point up there is 1e squared, right? Yes? Okay. So what's the integral that gives the area under that curve?
Integral from 0 to 1.
Yep, no trick question there. It really is just a pretty easy area. Okay, so that's 1/2 e to the 2x evaluated from 0 to 1, which I think ends up being 1/2 e squared minus 1, right? Or e squared minus 1 over 2. Then little m is rho times area, or rho times e squared minus 1 over 2. Okay. Ready to find mx? Okay. So mx is the integral from 0 to 1. Now that's the one that's rho over 2, f of x squared minus g of x squared.
Why don't you just go straight into finding x bar?
Can I? You totally can. The only thing is WebAssign is going to ask for it this way sometimes.
Oh.
Does that make sense? So we'll just do it this way because WebAssign will ask you to do some problems in these parts. But you're totally right. Just the next one will go straight to x bar, y bar.
Okay.
We'll do one each way. Now, in this case, what's your f of x curve? Who's your upper curve? E to the 2x. Who's your lower curve? Y equals 0. Okay, so if you have y equals 0, technically it's a curve. It's just not very curvy. Does that make sense? Okay. So that's rho over 2, integral 0 to 1, e to the 2x squared dx. Yeah, I'm going to keep saying rho, but it looks like a p, okay? So rho over 2, integral 0 to 1, e to the 4x dx. So what's the antiderivative of e to the 4x? 1/4 e to the 4x, 0 to 1. And we end up with rho times e to the 4th minus 1 all over 8. That's my mx.
What was g of x in that?
G of x was 0. Yep, and that would be not a bad thing for me to sort of notate that g of x is equal to 0. If there's no obvious lower curve, g of x will always be 0. I once made a mistake on a test and I said area between the curves, and I didn't, like, that person wasn't clear that she didn't get that it was 0. I felt really bad. My, so that's rho integral a to b x f of x minus g of x dx, right? And once again, g of x is 0, so you end up with x times x e to the 2x.
Y was the one that had the fx squared and...
You're just gonna have to memorize that, unfortunately. And for the homework, just look at your notes, right?
Yeah.
Okay, so what integration technique are you gonna have to use to do that guy? Integration by parts. So u is equal to x, du is equal to dx, dv is e to the 2x dx, and v is half e to the 2x. I'm just going to kind of like have that in a thought bubble or something. It's not terrible because it's good to review some basic integration by parts, right? Because that one's not a super hard integration by parts, is it? Okay.
If this is super hard, then the rest of the class is not going to be easy.
Exactly. Okay, so first plugging in 1 and 0 into the first part of the integration by parts expression, I think I just get e squared over 2. Do you guys agree? Because plugging in 0 does give you 0 in that case, right? Okay. This is going to become a quarter e to the 2x evaluated from 0 to 1, right? Be a little bit careful with negative signs there. Rho e squared over 2 minus parenthesis quarter e squared minus a quarter. Do you see what I mean about being careful with parentheses there? Okay. So if I have an e squared over 2, and I take away a quarter e squared, it's a quarter e squared, right? Okay, so that's rho times, well, I think that's just e squared over 4 minus a fourth then, right? Oh, it would be plus a fourth, yes, good. I was testing you. P times e squared plus 1 over 4. As we tell me to be careful with negative signs, and I myself wasn't careful with my negative signs. Bad. Okay, so this thing was mx, right? This thing was my, yes? Okay, so then the last thing we're going to do before we go cry in a hole is we're going to find x bar and y bar, this is easy. So x bar is m which? My over m. So that's rho e squared plus 1 over 4. I don't know why, I just wrote another row. Row your boat. Sorry. It happens. Divided by, what was our m again? Rho e squared minus 1 over 2, is that right? Okay. So first, the rows, goodbye, right? So I think we just end up with e squared plus 1 over I made a mistake.
Did you kill a kitten?
No, I didn't kill a kitten. It's a silly mistake. No, I guess it's not a mistake. Never mind. I lied. Okay, sorry. Backtrack. No mistake. It's perfect. Over. I was looking at the wrong thing. Over 2e squared minus 1. That is right. Woo! Nope, made no mistakes. Perfect. That's me. I love it, you guys laugh.
It's really easy to kill kittens starting with that word.
All right, so y bar. Y bar is mx over m, which is, okay, so mx was rho e to the fourth minus 1 over 8 divided by rho e squared minus 1 over 2, right? So the rows cancel, don't they? We definitely have an e to the fourth minus 1 over e squared minus 1. There's also a number in the denominator. What's it going to be? 4. Okay, awesome.
It's gonna be like one problem.
For the test, there'll be one problem like this. But the thing is, let me set up the next one a different way. It's a little bit faster, and I'll tell you what I mean, because there's a faster way to set it up. Okay, now there's one more thing you can do to this expression, because it can be simplified. Does anybody see it?
E squared plus 1 times e squared minus 1.
Do you guys see what he's saying? 4e plus 1, e minus 1, and then what else can factor some more?
Wait, can't you just say e squared minus 1 and then cancel?
Oh yeah, you could just cancel that out completely, sure. So e squared plus 1 over 4.
Yeah,
Yep.
it's a little bit fast than whatever you're doing.
Whatever, I was going to take it one step further, which was silly. Yeah, e squared minus 1 over plus 1 over 4. So it's really, really far, I think, faster. Instead of doing mx and my all separately and doing all that crap, I think it's easier to do these steps. 1, find a, okay? That's step 1. Step 2, use x bar is 1 over a integral a to b x f of x minus g of x. And then y bar is equal to 1 over a integral a to b f of x squared minus g of x squared. As in, just use those formulas.
Is there one?
There's also 1/2 in there. Yep, that's what I almost thought I missed in the last one. Thank you. So you find your area, and then 1 over a just takes that area and reciprocates it, right? Does that make sense? So, it's just that sometimes WebAssign will not let you do stuff that way, because it's going to ask for mx and my in 2 separate steps. Okay. So let's do this next one that way, okay? We're going to ignore their directions, and we're just going to find x bar, y bar. All right. And by find, I mean I'm going to set the integrals up and then tell you what to do with them. So you have sine x and cosine x. All right. Here in Calculus 2, you have to know how to graph sine and cosine. It's like minimum requirement out of you. One of the many.
There's going to be so many. If you had the question, you would tell us between 0 and pi or something. Right?
Well, you're going to see that they intersect someplace, and you'll find the point.
They're going to intersect again and again and again.
Yeah, I should give you an interval. Okay, you're right. They're going to intersect again and again and again. Okay, so there's sine. So I should label my graph. That's, yep. I must have left out part of the directions.
Or not thought there needed to be one.
No, there should needed to, I probably was supposed to give an interval or something. I don't know what happened. Because it definitely was saying 0 to pi quarters. So that's definitely what I was trying to do. So the area is going to be the integral from 0 to pi quarters. That's where sine equals cosine. And which curve's on top, which curve's on bottom? Yep, so we have cosine x minus sine x. You do that, and you get root 2 minus 1. Just gonna have to trust me on that one.
Why would it be squared?
Hmm?
Why would it be cosine squared and sine squared?
It's the area, not the volume. You're thinking about what if you rotated it about an axis and you found the volume of it.
Because
the-
you said and it was on plate, so there's difference.
Yeah, but in doing that plate calculation, like in finding x bar, y bar, I have to find the area as part of the question. Like the formulas both have this 1 over capital A in them. So the formula for x bar, for example, is 1 over capital A, integral A to B, x times f of x minus g of x. Right? That's what you have in your paper? And this A, that capital A, stands for what is the area of that region you're looking at. So you have to find the area to do the rest of the problem. Okay, yes.
So wouldn't another way to derive my or mx be you multiply x bar times the mass?
Probably, but I think I don't want to take the time to answer. I'm not sure, okay? I think we might have done that in the derivation. Okay, then x times what goes in there now? So f of x minus g of x is cosine x minus sine x.
And it's top minus bottom.
It's always top minus bottom, yep, because it was the top curve, is the derivation was f of x was the greater curve, so it's top minus bottom. Now at this stage, you'll do integration by parts. Does that make sense? And you could do integration by parts on 2 integrals, but it will also work if you do it on 1 integral, and you let u equal x, du equal dx, dv is cosine x minus sine x, and then v is equal to what from there? Sine x plus cosine x, right?
Why can't you just do u sub? Oh wait, you still have x. Never mind.
Okay. Does everyone agree that that's the right way to proceed, though?
Yes.
Okay. And when you do that and do much tedium and plugging in the calculations, okay, because I'm not going to show you enough time, you end up with 1 over root 2 minus 1 times pi root 2 over 4 minus 1. That's your x bar. The notes online show all the steps to get there if you want to see them, okay? It's just making sure you keep track of signs correctly and plug numbers into trig functions correctly. Okay, y bar is going to be 1 over 2a, so that's x bar. Y bar is 1 over 2a, integral a to b, f of x squared minus g of x squared. So that's 1 over 2 times root 2 minus 1, integral 0 to pi quarters. So cosine squared x minus sine squared x, right? And there's an identity for cosine squared minus sine squared, but personally, I don't remember it. And if you don't, but you remember how to deal with cosine squared, what do you use for those? It does equal cosine 2x. It's actually 2 cosine 2x. So here's why. Don't multiply. No multiplying. No. When you see cosine squared and sine squared in section, what was that? 7.2, how did we deal with them? What did we change them into? You use the half angle things, right? We did 1/2. This would be 1 plus cosine of 2x minus 1/2, 1 minus cosine of 2x. Back. Okay, good. it's still going. Cosine.
Did you change the balance?
Nope, did not.
You're still using the same gradient.
Yep. Didn't mean to change the bounds. Okay. And then think about what's going to happen inside of that integral. So the 1/2 will distribute. What happens to the positive 1/2 and the negative 1/2? They cancel, right? And then you end up with 1/2 cosine of 2x plus a half cosine 2x. So you were right. This is just cosine of 2x. But my point is, you don't have to have that formula memorized. If you do, great, like you're faster for it, right? But if you don't, just know it. If you see cosine squared, change it into 1/2 1 plus cosine 2x. That's kind of like the basic thing you should know how to do. If you know more trig formulas, it's just icing on the cake. That's totally fine. I'm not going to dock you for being smarter than me. Is that all right? Okay. And when you work that out, blah, 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 you end up with the fact that y bar is 1/4 root 2 minus 1.
Certain aspects keep popping up in all of
The theorem of Pappus is so cool, except for it's just like we're out of time. Okay.